I actually, before we jump into discussing machine learning, deep learning, I would love to ask you a couple of questions. So, based on a lot of questions for our previous presenter, you guys, most of you, doing machine learning, right? So raise your hand if you believe that you're trying to solve machine learning problem. All right. How many of you guys are actually solving deep learning problem? Not that many. Okay. How many of you guys heard about Berkeley's Caffe deep learning framework? Same guys, okay. So we're going to be talking about deep learning today. So the difference between machine learning and deep learning is, well, I guess it's settling right now. In my mind, deep learning is more compute-bound type of problem where you need, for instance, classify images, recognize voice, do speech recognition, and Caffe is one of the frameworks used for it a lot. And what we will be talking about today is how this framework can be optimized for Intel architecture, how you can get better performance. And we are talking not by 5 times, 2 times, hundreds of times better performance on Intel architecture, but by just applying simple, common, modern code techniques, parallelization with multi-threading, vectorization, and so on and so forth. So that's what we will be discussing today. I should probably tell you a little bit about my background, this 3 letters PhD. I actually got a PhD in physics, but I've been using deep learning for recognizing 3D structures of proteins. I was doing molecular dynamics simulations. And while actually optimizing some of those physical workloads, I got familiar with the modern code techniques, meaning parallelization, distributed compilations in the cluster environments, and well, that's I guess why Intel decided to hire me, right? I became modern code developer evangelist. I've been traveling all over the country doing lectures and teaching students and professors about how to optimize their code for better performance. But recently, Intel decided to actually take a closer look at machine learning workloads, deep learning workloads, and because I had some deep learning backgrounds and I applied deep learning techniques, I became also evangelist for those problems as well. So today we will be talking about image classification. That's what Caffe framework is really great for. We'll discuss how this code, how the implementation of the framework itself can be optimized. Right, so I will give you just first kind of idea why, for instance, our competitors, I would prefer not to call them, can claim that they have thousands times better performance compared to code running on CPU. Well, if you comparing highly optimized code with unoptimized code, well, of course you're getting this amount of huge difference. So if you actually optimize your code, if you use vectorization, multi-threading, you can get pretty close. So that's what we will be discussing in the second part, and I will show you how actually Intel engineers applied those optimization techniques to get better performance out of Caffe framework. And also I will give you just overview where Intel is going and how we want to create the whole ecosystem around machine learning workloads, deep learning workloads, and what options you guys have. All right. So if we just take a look at our modern Intel architectures, 3 main levels of parallelism should be utilized to get better performance of your code, any code actually. Vectorization is basically your operation on multiple data points simultaneously with the same instruction. Those instructions called CMD instructions, which stands for single instruction, multiple data. So that's just alternative instructions to Scalar instructions where you just simply take multiple numbers and process them simultaneously, right? So you're basically getting this data parallelism on the level of one core. Next level, you have multiple cores on your modern CPUs. And utilizing multi-threading allows you to basically use all of those cores or maybe even multiple sockets, right? Because our modern motherboards, they can support multiple sockets on the motherboard, 2, maybe even 4, and utilization of all of those cores and all of those sockets with multi-threading allows you to use all of them. And finally, distributed populations, where you have multiple machines in the cluster environment using MPI, for instance, message pass interface, or other libraries available. You can distribute your population to multiple compute nodes. So today we will be mostly discussing first two parallelizations. So we'll talk a little bit about data parallelism with vectorization, and I will spend majority of my presentation time on multi-threading. And distributed completion, I think it's really interesting topic, but it will take me probably a couple of hours just to cover all available options, so we're not going to go there at least today. So that's a little bit brief introduction into what will be covered, and why do we care, right? Why do we care about the performance? Well, let's just take a look at the previous Intel architecture products. Different processors, for instance, were released in the last couple of years. You can see that number of cores, and I can actually use my umbrella for that. Number of cores increasing almost exponentially. So right now we at the point where on Xeon Phi processors we have more than 70 cores, physical cores available, with 4 hardware threads on each core. That basically gives you a couple of hundred threads available on one processor. That's a huge amount. Also, number of widths, well, basically CD widths, number of well, data points you can process simultaneously, increasing as well. Right now we up to 512 bits wide vector registers. You can pack up to 16 single precision floating point numbers into one vector register and process 16 numbers simultaneously. If you're working with double precision, you can pack up to 8 numbers there. So if you just think about it, multiply number of threads by 16, that's how many numbers you can process simultaneously, you get a pretty huge amount of calculations available to you. Without using Scalar, so using Scalar instructions and using only single thread, meaning single core, that's the performance you will get, right? By using vectorization and parallelization and spreading your calculation to all of those hundreds of cores, you can get more than 100 times better performance of your calculation. So when somebody's claiming that their calculation is 1,000 times better, they basically compare this Scalar single-thread implementation with their optimized technology. So today I will try to explain to you how we can actually get to this point where we're using vectorization and parallelization with multi-thread. All right, so let's start from the beginning. What is Caffe? Caffe is a deep learning framework which has been developed by Berkeley students. They started this project a couple of years ago, and it's open source, so it's publicly available on GitHub, and you can just download it and play with it. But those students were developing it with CUDA in mind because they were, this language, well, yeah, I can probably call it language. CUDA was something they used to, and they implemented CPU version, but it wasn't optimized at all. And it took actually Intel engineers, to jump in and look at this CPU code and optimize it for modern Intel architecture, apply vectorization, optimization techniques, apply multi-threading, and currently it is available on GitHub as well. So if you're interested and want just to use this framework on regular CPUs, you're free to do that. Just go to GitHub, download this repository, and use it. Also, installation process and explanation of all the layers and the components available on our IDZ, Intel Developer Zone. Andres Rodriguez, a friend of mine and colleague, he actually wrote this article where he explained how to install this framework and how to use it. What I will try to show you is if we just take some data sets. In my case, I decided to go with Scalar 10. It's a simple data set of 60,000 images, pretty small images actually, 32 by 32 pixels in RGB format. And we have 10 different classes. So those classes listed here. So we have images of airplanes, birds, cats, deers, dogs, and so on and so forth. So it's a really small data set relative compared to, let's say, ImageNet or others. But it's usually used to kind of test your topologies, for instance, or just test your framework. So I've decided to go with this particular framework, data set, just because it was kind of relatively small, and I can still analyze the performance of our framework and compare how this performance will change if I use optimized version of Caffe. So if you want to play around with this data set, it's also publicly available from Toronto University website. You can download it and play around with it. That's probably too small for you to read, but that's the original measurements of time we spent on each layer, and that's the explanation of each layer. By the way, how many of you familiar with the deep learning terminology? What is layer? 4 guys. Yes. So basically, when you're doing convolution, you're starting with just image, convolve doing pooling. So each of those operations is called layer. So at the end, you're kind of reducing to just labels, and at the end, most probably you will have kind of fully connected layer and something like that. So with the Caffe, if you just simply run Caffe with the time parameter and specify model and number of iterations, and then you can see how much time you spend per each layer doing forward and backward propagation. Once again, if you're not familiar with these terms, forward propagation, that's your inference, or you're just doing the estimate or trying to predict a particular outcome for your image, or what will be the probability of this label to be applied to this particular image. And for the backward propagation, you're just calculating all the derivatives to well, adjust your weights, adjust weights of your convolutional neural net. So in our unoptimized case, we actually spent 270 milliseconds just doing forward and backward propagation. At the end, I will show you that this number can be reduced, I will show you later, to something close to 20 milliseconds. So basically from 270 to 20, and for this particular case study, I was using just regular Xeon CPUs. That's a single compute number. For KNL, this number will be even more dramatic. But this study was done about, I believe, half a year ago. So I have numbers for KNL, and I was actually planning to show you a real live experiment, just connecting to KNL, but unfortunately my computer went down, so maybe next time. All right, so for our profiling, we usually use tools, profiling tools like VTune, for instance. VTune amplifier. It allows you to actually well, create timelines of utilization of each individual course. And right here, I'm just showing you how course threads utilized on an optimized version of the Caffe. All of those, I guess it's orange spikes, that's correspond to just spinning time, and legend is right over there. So our original code, it was running on 36 physical cores. But at the same time, those cores, they were just simply doing nothing. They were just spinning, and they were utilized only briefly, and surprisingly, it was for the matrix multiplication. So only at that point when we were doing convolution, that's where they were utilized briefly for a fraction of a second, and then they were just spinning and once again doing nothing. And we spent majority of the time just on synchronization of those threads. So if we just look at the VTune results, you can see that that's our histogram of utilization of the cores. So in ideal parallel code, we should see only one spike right here. For my system where I have 36 physical cores, that's where it should be. Unfortunately, it's all right over there, and basically only a single thread is usually utilized. So we're dealing with not parallel, not optimized code at all. And just for your reference, that's the description of the system I was using for the testing. So I have a dual socket Xeon processor with 18 physical cores per socket, so 36 physical cores in total. Hyperthreading was disabled. I think for this particular CPU with enabled hyperthreading, I would have seen about the same performance. So hyperthreading right now, previously in HPC, and I have HPC background, so I can tell you for sure. Previously, there was a claim that for high performance applications, hyperthreading were slightly well, first of all, it can limit the amount of cache volume available to you. And also the switching between threads it's really good for latency bound type of application, but not that great for compute bound or bandwidth bound applications. Although it's not the case for modern CPUs because there's pretty much no cost in switching. So I still see a lot of clusters, HPC cluster, disabling hyperthreading by default. It should probably be enabled just because for latency bound application where you have random access to the memory, it will speed up some of those calculations. Just, sorry, side note. So for the conclusion, if we take a look at the time distribution and thread actually utilization, we can definitely tell that we have insufficient multi-threading scalability here. And just if we take a look at the hotspots, basically that's your functions where you're spending most of the time. The one takes the majority of the time, which is 1,130 seconds, is a P4 barrier. It's basically the function of synchronization between your OpenMP threads. So what I'm claiming here is that multi-threading, which is used for matrix-matrix multiplication behind the scenes, is actually slowing down our compilations. Just because we need to reinitialize those threads, do the compilations, and move the data to the corresponding thread stacks, and then kind of reduce the compilation back. So how we can check this theory? Well, we can probably just use environment variable expert OMP num thread and kind of force OpenMP just to run the whole code using single thread. So my calculations, my time of the calculations actually reduced from 37 seconds to 31 seconds. So that basically proves that our multi-threading, which is used by MKL library, which is used by Caffe, not by default, but I was looking at math kernel library, it was actually slowing down the calculations. So we need to actually work and parallelize not this matrix-matrix multiplication, but move this parallelism to the upper level. So maybe split the images we process, right, in parallel, and do this in parallel, and so on and so forth. So the scheme of the parallelization should be changed because the way it's implemented right now is definitely not working. All right, so what else? We can take a look at the hotspots, and hotspots, that's basically your candidates for the scalar optimizations. That's the functions where you're spending majority of your time. And in my single-threaded implementation, I was spending a lot of time in single precision general matrix-matrix multiplication, or SGEM. But it's been already optimized, right? Because we're using SGEM from math kernel library. Intel engineers spent years optimizing this thing, so I definitely will not be able to beat those guys. So we will leave SGEM alone. But there is IAM2call, a function which actually converts our original image. It kind of pre-formats it for the convolutional operation next. So what it's doing, original image, with a convolution, you just apply a filter to one particular spot, then shift it by next sprite, and so on and so forth, right? But what you can do, you can simply copy some of those pixels and put it right next to each other, and then just apply simple matrix-matrix multiplication. That's what we use for convolution right now. And it's pretty smart, right? Because we already kind of optimized our matrix-matrix multiplication. Why not just use it? So this additional function, IAM2call, is doing exactly that. It kind of preforms our images to this particular format so that we can use matrix-matrix multiplication later on. Pooling layer is simply used for reducing dimensionality. So if you have pretty big image, right, maybe if you just shrink it by 2 times, the useful information still might stay there. And that's the trick is used to reduce dimensionality for our after convolutional operations and still get labeling at the end. All right, so for those operations, we'll actually take a closer look at the code implementation and try to parallelize them. And what I will show you, probably counted with those numbers, but at the end, yes, we actually getting 20 milliseconds when we apply all of those optimizations. So it's about 13 times better performance on my dual socket Xeon CPUs compared to the original unoptimized code. And what we did, we simply applied scalar optimizations. We used multi-threading inside the layers to parallelize some of those workloads. And for the vectorization, we use just-in-time assembler. It's actually an open source project, which allows to simply for some of those operations, mathematical operations we're using inside those layers, apply CMD instructions. So it's actually a pretty standard approach, and Intel call it modern code approach. We're just looking at all of those kind of layers. So first of all, if you just using mathematical routines, standard routines, maybe you can just leverage some of those already optimized workloads, some of those optimized functions. For instance, MKL, Math Kernel Library. It's already have a lot of optimized routines which use multi-threading and vectorization kind of things. But if you're doing something unique, you can take a look at your code and apply all of those additional optimization techniques like scalar optimizations, vectorization, multi-threading, and finally scale your application to all of those compute nodes you have in your cluster. All of those techniques actually covered in our course. If you're interested, any of you interested in high performance computing or optimizing your codes? A couple of guys, okay, great. So in this case, just go to software.intel.com/modern code. On modern code, we have the whole training. It's about 5 hours of video material, which we simply discuss how to optimize your code with practical real-life examples, code samples, and you can even download those samples and play with them on your own machine. All right, so let's actually dig deeper and look at some of those serial optimizations. So for serial optimizations, we reduce algorithm complexity, reduce the amount of calculations, and unwinding some of the loops. So let's take a look at the second point, reducing the amount of calculations. So let's say what we have is just we're going through our image, right? That's why we have 2 for loops. In outer one, we're just going through the height with the basic layers of rows of our image, and width. So basically, we're looking at the columns. Can anyone tell what's wrong with this particular code? I know it's pretty small, but anyone? All right, I'll tell you. We're actually doing calculation for HIM in the innermost loop. And this calculation will happen on every iteration of our innermost loop. But it doesn't really use iterator. So what we can do, we can actually move those calculations outside and reduce the amount of arithmetic operations we apply in the innermost loop. Really simple, but surprisingly, that can speed up your code by a factor of 2, 3, 5 easily. So that's one of the optimization techniques Intel engineers did when they look at the source code. Next, CPU-specific, system-specific, and other generic code optimization techniques. They looked at the IAM to call, remember this function which actually pre-forms the image for convolutions. Other avoid thread movement. Actually, when you, by default, every operating system will not allow application to run on the same core for longer than, I believe, 5 seconds. For Linux kernels, that's about 5 seconds. It will simply try to migrate it to some other core. Why is doing this? Well, I guess if you have single-threaded application, you want to kind of spread your population all over physical devices to distribute the heat, right, generated by the CPU. But when you have HPC application and all the cores is utilized already, surprise, surprise, you still will be moving your threads around. So you don't want to have this behavior. Why? Because as soon as you move your calculation to a different core, all the stack will have to be moved. And all the caches will have to be repopulated, right? So you spend a lot of time having those cache misses. So that's why pinning your thread to a particular core is actually quite beneficial. All right, another calculation. So let's try to guess what we can do with this particular one. We have 3 loops, right? And once again, we're going through the through the pixels, right, of our image, but also we're going through different layers of this particular image. And then to find the value in this particular pixel, we have to do multiplication, addition, another multiplication, and another addition. So we're actually doing a lot of calculations, which are not needed. Because in those three for loops, what we are doing, we're just simply looking at the next pixel. Why don't we just simply combine those three loops into one, and then just go through all of those pixels sequentially? In this case, we can also reduce the amount of multiplications and additions we have. So yes, you can actually simply do one addition plus one and go to the next pixel, right? And have only one conditional branching to check if you're already at the end of your last layer, last pixel, and then exit through for loop. So another optimization, scalar optimizations you can apply. Our engineers actually looked at the conditional branching. So when you have logical expression like that, we're just simply checking if our x, our pixel, is larger than 0 but less than n. But you can simplify those operations because right here you have two comparisons and then one AND operation. You can reduce it to a single comparison with the typecasting. Just because we know that n is always positive, we just need to check that x is positive and then just do the comparison. So some of those logical operations also can be optimized, right? So, well, it usually helps if you have some background in HPC because you're basically trained to spot those optimization candidates and then apply particular techniques. Like in this case, we're just converting our integers to unsigned integers and reducing the amount of comparison we actually do. All right, so that I'm done basically with the scalar optimizations. So at this point, our code has been already vectorized and we optimized some of those calculations. Well, most of the times we just simply reduce the amount of calculations we were doing. Next, let's take a look at the code parallelization with OpenMP. How many of you guys heard about OpenMP library? Intel guys, okay, I know you heard about that. Cool, okay, so some people know about OpenMP, and that is simple library which allows you with pragmas simply parallelize your calculation to multiple cores or multiple threads, right? So what you can do, you can simply put pragma OMP parallel for on top of your for loop, and then iterations of this for loop will be distributed to how many cores or how many logical threads you have in your system, and those calculations will be done in parallel. So if you don't have any data dependency, if those iterations can be processed in parallel, you're done. You basically just parallelized your for loop for multi-threading. If you have data dependency, that's the tricky one, because in this case you will have to be careful about specifying shared and private variables or doing proper reduction, but that's a topic for a completely different talk. And it's probably going to take me 2-3 hours just to cover all of the basics. But OpenMP library can be applied to all of those layers implemented in Caffe framework, so convolution pooling, deconvolution, LRNs, reuse, softmax, and so on and so forth. So that's one of the examples of the code. I hope you guys can see it. So in this code, what we are doing, we simply have a for loop where we're going through, I believe that was number of images. So we're simply applying forward propagation, forward gem operation for our image. And what we do here by providing pragma OMP parallel for on top of this for loop, which is parallelizing these operations. So our images process one image per core in parallel. As simple as that. Surprisingly, that can give you, what, 16 times better performance, right? Just because you're utilizing all of those available cores, and instead of them just spinning, waiting for new workload to appear, they will be processing their own image. And those type of operations were applied for a lot of different layers. So for instance, for pooling, for subsampling, also parallel parallel 4 with collapse. If you're not familiar with this particular clause, it simply combines two for loops together, and then iterations of all of those two loops will be spread among available threads. And we do generator function here. So whenever you have independent operations, it's pretty safe to parallelize them. And just by simply putting parallel parallel 4, you can do this. You can spread your calculations to multiple cores, spread them among available threads. Have a couple of more examples, like softmax, for instance. All the operation, so in this case, division operation, were spread among available threads. ReLU operation also being spread, and we're using actually standard library for that, softmax at least. So simply by looking at the code, you can parallelize those operations if you don't have data dependency. So that's actually one of my last slides. At the end, original calculations, if you remember, they were taking 37 seconds when we had multi-threading, 31 seconds when we disabled multi-threading by using OMP non-threads environment variable. Now this calculation time reduced to 3.6 seconds. So it's overall time with all data preparation and so on and so forth, even that time included, the time of the calculations were reduced by a factor of 10 before. And you can see the distribution of